In this video, we will be talking about cross-validation. When performing machine learning evaluation, then the simplest and the most recommended approach is to use a training, dev, and test split of your data. But this is not always possible. For example, if your data is very small, then separating some of it for testing doesn't really work well. Let's say you have 100 examples and you separate 10% of it for testing. That's only 10 examples, and it's not really enough to draw any conclusions from that test set. You could try increasing the proportion of your test set, but let's say you go to 50%. Now you have 50 examples, but that's still not really enough for a proper test. And at the same time, you now only have 50 examples for training your model. And that's not enough to train a machine learning model. So we can use a different approach in these cases. And one approach that we can use is cross-validation. Now, the idea with cross-validation is that instead of dividing our data into training, dev, and test split once, we do this many different times and we create many different splits. So we take our data set, we separate it into k folds. It's very common to use k equals 10. So we separate our whole data set into 10 different parts. And then we select one for testing. We train on everything else. And we evaluate on that data, and then we rotate. So if we look at the diagram here, we take our data set, we separate it, so we have this part for training, this part for testing. We get some kind of result from training our model and testing it on the yellow part of the data. We then move on, we take the next part of the data for testing, and we again train on all the green parts, so here and here. We train our model on these, and then we test on this data, it was previously part of the training data, but now in this fold we are using it as the test data. And we do this as many times as the number of folds that we have separated our data into. So by the time that we're done, we will have used the whole data set for testing. We have tested on every part of the data, but at the same time, we have never used the same data point for training and testing at the same time. And then in order to get an overall result after doing these 10 experiments, we just average them together. So we take the individual performance metrics, whichever they are. They can be errors, accuracy, F-measure, and then we just average them together. And it's important to note that cross-validation is a method of evaluating an algorithm as opposed to a particular model, because you don't evaluate one trained instance of the model. You train 10 different models and you get 10 different results. So you can't say that this particular model has a particular performance. What you can do is you can determine that the general approach and the general algorithm has a particular performance. When performing cross-validation, then sometimes we still need to do some parameter tuning. And so how do we do that? Because now we have so many different train and test splits. Well, option one is to extend the same idea of a three-split approach to the data. So instead of just having training and test separation at each fold, we take one part of the data for testing, we take one part of the data for validation, and we take all the rest for training. And then when we rotate the test part of the data, we also rotate the validation part of the data so that we never use the same data for training and validation. We never use the same data for training and testing. This is a possible approach. The issue with this is that you're still going to be running into the problem of data sparsity. So you've kind of solved the issue with having a small amount of test data, but if you're tuning your parameters based on the validation set in each split of the data, then this part is still going to be very small. So it might not give you representative results. An alternative approach that we can take is to do cross-validation within cross-validation. So this requires a bit more work, and it requires a lot of experiments, but it will likely lead to the best results if you do need to do this on a small data set. So essentially the way that this works is at each fold of the cross-validation, you first separate one part of it for testing. So let's say this is fold 1. And in fold 1, you separate the yellow part for testing. And then you run cross-validation over all the rest of it. So it's this part here. This internal cross-validation allows you to choose the best hyperparameters for your model. And then once you have the best model, you then test it on the yellow part of the data. And then this gives you the result for that particular fold. You then move on. You take for fold 2. For fold 2, you rotate the part that you use for testing. So now the yellow part is again for testing. And you run internal cross-validation over all of the other data that you have. And again, you get a new result, you get a new best configuration for your model, and you get a new evaluation. And once again, when you're completely done, then you just average the results. And worth emphasizing again that even more than before, you definitely are not evaluating one particular model when you're doing this, because in this case, you're actually, and you will be using different hyperparameters even for each fold of the evaluation. So you're essentially in each fold, you have different model configurations. So what you are really evaluating here is how well the overall approach to solving a particular problem works. Also worth noting that this isn't practical in all situations, because it does require a lot of computation. Let's say you split your data into 10 folds. Now you will be running 10 experiments on the outer part of the cross-validation, but if you run an internal cross-validation for parameter tuning, you might end up with 100 experiments in total. And running 100 experiments, this can be quick if your model is really small and your dataset is very small. If your model is quite complicated and training takes time, then training 100 models is not always feasible. Now, once you've done all your evaluation, you've found the best hyperparameters, you have an estimate of the performance of this model, there is an optional step that you can take, which is you can take your whole dataset, train your model on the whole data in order to get the best results. So this is something that you would normally do if you were building up an actual system that goes into production as a product, for example. This is not something you would do for research. For research, it's more common to just keep separation between training, development, and test data. But for practical applications, it can be important to squeeze every little bit of performance out of the model. And doing this, you can achieve that. If data is really important, then excluding 20% of it for validation and testing can make a few percent difference in performance. So you can reclaim that unused data at the very last stage. The bad aspect of doing this is that you no longer have a way of estimating how good your model is on held out examples. Because you've gotten rid of your test data and you don't really know, you can't be sure how well your final model performs. You are kind of hoping that because you've tuned the hyperparameters, these hyperparameters generalize to this new model as well, but there will always be some variation. So it's a trade-off between the two aspects. So in summary, when performing machine learning evaluation, if possible, it's recommended to split your data into training, development, and test set. Then you train your model parameters on the training set, you tune the hyperparameters on the validation set, and you get a final performance that represents how well your model performs on held out data using the test set. If that's not possible, if your dataset is very small and results on the test set would not be meaningful enough, then we can turn to cross-validation. We separate our data into many parts. We train on most of it and test on one particular fold, and then we rotate which fold we test on. And we end up testing on the whole dataset, which gives us a better representation of the results.